So this is a continuation of where we stopped last time, taking you guys through the problem solving of selected questions in your problem sets, so that hopefully everyone is on the same page, on how to solve some of these problems, especially in light of the coming midterm exam, which is only in about 2 weeks or so. So I think we left it at question number 11 about the figures of merit. And so today we're going to complete, the selected questions that I have. So let's look at question number 12, which is not very different from what we had solved earlier regarding back titration. And the back titration we are talking about, is a Volhard method, which I've covered, in previous lectures. Now, remember, the reason why we back titrate is because of a couple of reasons, such as if you do not have an appropriate color indicator for a direct titration, maybe you need to do a back titration. If also you have a direct titration reaction that doesn't have a very big equilibrium constant, meaning that the products are not favored, then you need to do a back titration. If the reaction kinetics, of a direct reaction are not fast enough, then again you need to do a back titration. And remember, ideally, if at all you're doing a direct titration, you need to make sure anytime you add a very small drop of your reactant, the reaction goes to completion. If that's not the case, if you need to wait for 2-3 minutes, then a direct titration will not work, and instead you would do a back titration. So an example of a back titration is a Volhard, method, which is an agentimetric, titration. Now, so in this case, you've got, the chloride. You've got the chloride, which is the unknown sample. And you're reacting it with the titrant, in this case, which is silver. And so that is a titrant. Now, agentimetric titration largely means, that the titrant is silver. That's what agentimetric titration means. And because we are doing a back titration, we're gonna add, silver in excess in a beaker. So you take, say, chloride sample, maybe it's a water sample in this case, and you add the titrant in excess, and the reaction proceeds. You give it enough time, you give it enough time for it to proceed to completion, to give us, the salt, and the excess age silver that is remaining, okay, because we added in excess. Okay, so how you then calculate then is to determine the moles of what you added, which is equals to the 50 mil in this case. That's what you added, and then you multiply it by the 0.1214 molar. That's what you added of the silver nitrate. And when you calculate that, you're gonna see the number of moles in millimoles. In this case is 0.07 millimoles. Okay, now after you do this, you're gonna react then the remaining silver, which is that, and then you're reacting it with the thiocyanate, which is the next titrant, that you're using. And in this case, you get the silver thiocyanate. And in fact, in this case, you don't even need an indicator, because this guy is fairly colored. So you can see we've got now the next, titration here that is taking place, where you are titrating, the excess silver that is remaining, that did not react with the chloride. and you're titrating it with a thiocyanate, to give you the silver thiocyanate. And so in this case then, I calculate the number of moles, that were used to titrate this, which are already given up there, is equals to 11.76 mils. That's what was used. And the concentration of the thiocyanate was 0.1019 molar concentration. And when you do that, you get 1.1983 millimoles. Okay, so remember, this is a one-to-one stoichiometry. It's a one-to-one stoichiometry. It's a one-to-one stoichiometry. Meaning that the moles of silver plus that is remaining would be equals to the number of moles, of the thiocyanate that were consumed, that we've already calculated up there, which is 1983 millimoles. Meaning now we can calculate the number of moles of chloride, in the unknown, which should be equal to the moles of silver that was added in excess, subtracted, the moles of silver that remained. So essentially that should be the moles of chloride, that was really consumed, which is equals to the 6.07 millimoles minus what remained, which we've already determined from the next titration, which is 983 millimoles. And when you do that, you get 4.8716 millimoles. And of course, the question being asked is the percent chloride, that is present. And the percent chloride, is calculated, by calculating the grams of chloride, which is equals to the number of millimoles, which is 4.8716 millimoles, times, the atomic weight of chloride, which is 35.45 milligrams per millimole, which is the same as grams per mole, and when you do that, you're gonna get 172.70 milligrams. And then of course after that you can calculate the grams of chloride, which we know is equals to the grams of chloride that we calculated, divided by mass of sample, total mass of sample, times 100. And so in this case, you can just substitute, you've got 0.17270, that was the grams up there, divided by the mass of the sample, which we know is 0.8165 grams times 100. And you should be able to get 21.15 grams as what you would determine as a concentration, of chloride in the sample. So the next problem is fairly straightforward. You've been asked to titrate 3 different ions by a gentimetric titration relay, because we are using silver in all cases to titrate the chloride, bromide, and iodine, possibly, in a water sample. And the question is, sketch the titration curve, for that you get, from this kind of a titration. So the key thing here is, to remember what we talked about previously. What ion precipitates first? And remember, the ion that precipitates first, you'd be the one that has got the least molar solubility. Now, because here we are dealing with monovalent ions, all of them are in the same valency. The valency is -1. We don't really need to calculate, the molar solubility. Instead, we can determine the ion that precipitates first simply by looking at, the least KSP. So the one with the least KSP precipitates first. And of course, you can see the one that precipitates first, is the iodide, because it's got the least KSP. The next one, is the bromide. It's got the second, least KSP. And lastly, you've got the chloride, which has got the largest KSP. Now, take note of this. If at all the ions, had different valencies, meaning you had, say, -1, -2, and so on, in that case, you have to calculate the molar solubility. And of course, from my lecture, you already know how to calculate the molar solubility, which is a repeat of what you guys did in Chem 1 or 2 anyway. All right, so in this case, then you just need to plot, and simulate your titration curve, which in this case you've got volume of the silver, which is a titrant. And then in this case, you've got the negative log, of the silver. And that's what you are monitoring, as you do the titration. And so the curve is going to look something like that. Meaning, this is the VE1, which is a titration for iodide. This, the midpoint inflection, is a VE2, which is for bromide. And the midpoint inflection, in that slope, is equivalence volume, for chloride. And so basically, that's going to be a titration curve. And when you do it in the lab, you're going to see the titration curve typically should look like that. Possibly, let us simulate a titration curve, by looking at question number 14, which essentially is telling us, to simulate or to quantitatively simulate, really, a titration, the agentimetric, titration curve. So it's just meant to simulate the agentimetric titration curve. Remember again, agentimetric just means the titrant, it's silver. That's all what it means, okay? And so you've been given, a situation here where you've got chloride, and yes, titrating a standard, really, a chloride standard, and you're titrating it with a standardized silver nitrate solution. And the question is, calculate the chloride ion that is present in your Erlenmeyer flask at different intervals in the titration. And the intervals are, after I've added only 0.00 ml of the titrant, the silver, after I've added 10 ml, after I've added, 50 and so on. And the idea here is to simulate for you guys to see the theory, behind the titration that is taking place. Okay? So if you're given a problem like this, the first thing you need to do is to calculate the equivalence volume. And I already talked about the equivalence volume in my lecture, and I defined it, as the point at which you've added enough titrant, all right? So that's a titrant. and then you've reacted it with the chloride to give you the product, and the product is a silver chloride salt. And so the equivalence point is a point at which you've added enough titrant, to react with all the chloride, that is present in the sample. Meaning the number of moles of chloride, which is the unknown, should be equals to, the moles of the titrant. So that's what really equivalence volume mean. The situation at which, you've added enough volume of the titrant, to satisfy this situation. The number of moles of the chloride is equals to the number of moles of the titrant. And of course, this is a titrant. And this is the unknown, or what you refer to as the analyte. Okay. So in this case, then you've got you've got the 50 ml. It's already known. Yes, you're reacting as standard, really. In this case, that's a chloride. That's the number of moles of chloride, and the VE, is the equivalence volume. And the concentration of your silver, is equals to the 0.1 molar. And I think all of us know the C1V1 is equals to C2, V2 in this case. And C1V1 refers to the number of moles, right? Number of moles. That's how you calculate moles, concentration times volume. Meaning, the VE, of silver is equals to 50.00 ml. That's the equivalence volume. And so it's very important to know at what point do I reach, my equivalence volume. So the next step then is to calculate the chloride present, and this one is a bit trivial, after adding 0.00 ml, of the titrant. And of course, this one is trivial because you already know the chloride present initially is equals to 0.1 molar. And so the negative log of chloride then, which is a PCl, remember that refers to the negative log. That's a symbol for negative log. Is equals to the negative log of 0.1, which is equals to 1. Okay, so that is the PCl minus is equals to 1 at that volume. So the next question, part is what would be the PCl after adding 10.0 ml of your titrant. Now remember, in this case, and I think it's important to write what's going on, you've got the titrant, you've got the unknown, and the product, and I already know how much I'm starting with in this case. Let me just call it initial. So the initial in this case, the number of moles is 50 ml times 0.1 molar. And of course, you're going to see the answer here is 5 millimolar. Now, I've added, 10 ml at this point, and the concentration is 0.1 molar. And you can see the millimoles here is equals to 1 millimoles. And so my equilibrium amount then is equals to, for every drop that I add, all of it gets consumed. So it's 0 moles or millimoles. And then in this case, I initially had 5 millimoles, but I've already reacted, 1 millimole, because remember it's a 1-to-1 stoichiometry. This one has gone into consuming that. And so it's 4 millimoles. Okay, and of course, I have formed 1 millimole, of my silver chloride. For every 1 mole, of silver added, it consumes 1 mole of the chloride added to make 1 mole or millimole, the equivalent of the silver chloride. And so that's what it is. I've got 4 ml of chloride. So the PCl then is equals to the negative log of the 4 millimoles, and in this case I need to divide it by the total volume, right? The total volume, which is 10 mil. That's how much I added. But initially, remember, if you look at the problem, initially I had 50 mil in the volumetric flask, and so in the end, that's what my concentration. So that's my concentration there. And when you do that, you're going to see this concentration is equals to 0.0667 molar. And when you take the negative log, of 0.06667 molar, you get a PCl, of 1.17. Okay, and so at 10 mil, that is a concentration. So just confirm, because the next question is at 49.99 mil, what's the PCl? And again, it's the same thing, the silver plus, and I know I'm being repetitive here. Initially what I have here is a 5 millimoles, and then I've added 49.99 mils times the concentration, which is 0.1 molar, which gives me 4.99 mil, meaning my equilibrium amount, all of this is consumed, all silver is consumed. And then in this case I would have the chloride remaining is 5 millimoles minus 4.99 millimoles, which gives you 0.01 millimoles, right? And so the chloride then, I can squeeze it here, the chloride then that is remaining is equals to the 0.01 millimoles divided by the total volume. And the total volume, you can see I've added from the titrant 49, and initially I had 50, and that's the number of mils. And you can see my concentration here then is 0.0001 molar, and then the PCl, meaning the negative log, I won't repeat that again, the negative log, the PCl is equals to 3.99, and just confirm that the negative log of that. Now the other part is, what about at 50 mil, after I've added 50 mil of the titrant? So if you've been following, you know that this is the equivalence volume, this is the VE, and we all know the equivalence volume means that the silver plus the chloride, this reaction has gone to completion, meaning I just have products. That's all what's present in my Erlenmeyer flask. Okay. Now we all know, if at all I add a salt, meaning I just have a salt of sodium chloride, meaning if at all I've got a salt of sodium chloride, that is saturated in water, what happens? It's a salt, so it undergoes dissociation, the KSP, to give us the silver plus, the chloride. And so this is a prevailing, reaction that is taking place. Meaning, I just need to calculate molar solubility. At this point, at the equivalence point, if at all you're dealing with precipitation titration, at the equivalence point, all what you need to do is calculate molar solubility to determine the component species, that are present. And of course, we know the molar solubility is calculated from the KSP and its equilibrium expression, which is that, multiplied by that, and it's a 1-to-1 stoichiometry, meaning is equals to x squared, x number of moles of silver, number of moles of chloride, and so forth. So when you calculate it, you're gonna see 1.8 times 10 to power negative 10 is a KSP, and you're calculating the x squared, and you're gonna see the x then is equals to the root of 1.8 times 10 to power negative 10, and this gives you 1.34 times 10 to power minus 5 molar concentration. Remember, x is referring to chloride, so it's a PCl, then is a negative log of 1.34 times 10 to power minus 5, which gives you 4.87, and that is the answer, at the equivalence volume. So finally, what happens, after adding 60.00 mil, of the titrant? Okay, you can see, this is 10 mil after equivalence volume, meaning we are just taking the silver chloride salt that was maximally found at the equivalence volume, and we are just adding silver to it in excess. Of course, we know at the equivalence volume, that's what we were having, that's the reaction that was taking place, the dissociation, of salt. But in this case then, we are adding silver to the salt after the equivalence volume, all right? And you can see that I've added 10 mil in excess after the equivalence, multiplied by 0.1. Okay, so that's what I've added in excess. And if you do that, you're getting 1 millimole. That's what I've added to the silver chloride precipitate, after the equivalence. Okay, so essentially, I would like you to see that this one really is what you guys call the common ion effect, which we covered already, in the equilibrium introduction. So this one is a common ion effect problem, okay? And we know by Leitch-Tarius principle, the common ion effect situation, makes the salt less soluble. Because I've got an excess of this already, the equilibrium shifts in this direction. So you got less, of the salt soluble because the equilibrium shifts in the negative direction. So the change then in this case is I've got the salt, that I'm adding, the concentrated, silver to it. So the change in this case is plus x, and my equilibrium amounts would be initially I had this concentration, 1 millimole. When you do this, you're gonna get 1 millimole, and the total volume, it's 110 mils, right? Plus x, right? That's what initially I have, plus the x. That's what I have there. And this one is the x, that's my equilibrium, amounts there. And so then my KSP is gonna be equals to, the 1.8 times 10 to power negative 10 and 0.009091, that's after taking these ratio, plus x multiplied by x, you know, so that's my chloride, you know, and that's my silver plus, right? And then after that, of course, you know, I can solve this problem. Of course, we know it's gonna end up being a quadratic equation, but I can assume that 0.09091 plus x is approximately equals to 0.09091. The reason we are assuming that is because you're saying the dissociation is very insignificant, okay? And so, you know, 1.8 times 10 to the power of negative 10 is going to be equals to 0.9091x. X, right? You know, because if we neglect this, you know, we expand it, you know, you're going to get that. And so when you do the x, then you're going to find the x is equals to 0.0001407 molar. And remember, you always have to check the 5% rule. You know, so check if we should have made that approximation, 5% rule. You know, which means, you know, my number here, the 0.001407 divided by the formal concentration. And my formal concentration was 0.09091. And you can see I multiply that by 100 and I'm getting only 1.54%. And so you can see it's much smaller, you know, it's much less, you know, than the 5%. And so my approximation, you know, this approximation was correct. To make that assumption was correct. And so my PCl then, you know, is equals to the negative log of my concentration, which was 0.01407. And in the end, you know, you get 3.85. Okay. And so when you plot your curve, because that's what B is asking, when you plot your curve, you know, with a silver titrant and you're plotting the PCl, then, you know, you can see that in each of the steps, as you increase the volume of the titrant, you're increasing, you know, you're increasing the PCl. And of course, that's what's happening in this case. You're increasing the PCl, you know, and so you're gonna see, your situation is like this, you know, this being the equivalence volume, you know, the midpoint of your inflection being the equivalence volume, we know, which is 50 ml. So question number 15, I think I've beaten that to death. And so just check, you know, because I solved this already, a similar problem. Number 10 is exactly the same. So try that, you know, because I've already, you know, solved something similar to this, you know. So just try it, you know, compared to what I did in problem number 10. So the other problem that I'd like you to remind you, and we did this, you know, in the lectures, is you've been asked to calculate the sampling error if at all I've got a data set, you know, of pure iron that I analyzed, so I digested a pure iron standard, and then I also digested an iron ore. So this one is mined, right? This one is mined, and this one is just a standard that I made in the lab. And the calculation is determine the sampling error. So remember our relationship, and you can check the notes, you know, sampling error squared or the standard deviation, really, that which is error is a standard deviation. That's what error means. Standard deviation is equals to the total error squared minus the measurement error. Error squared. Okay. Now we know that this one is obtained, from a heterogeneous sample. In this case, the mining, because it's a sampling, it's a real sample. Whereas this one, I just did it in the lab. I took a pure standard of iron. And so this one is obtained, from a pure standard. Referring to this data set. Okay. And so how do you calculate this? Again, fairly straightforward. If you calculate the mean of this data set, mean of the ore, let me just call it x bar, of the ore, is equals to 19.58. Just confirm that. Whereas the mean of this, of the pure one, is equals to 19.238. Okay. And then after that, if you calculate the standard deviation, you're going to find the standard deviation of this is 0.7285, whereas the standard deviation of this, let me just call it S, if you don't mind, S, is equals to 0.3236. It is best, to work with relative standard deviation. So calculate the relative standard deviation percent, which is equals to, you take the absolute standard deviation, divide by the mean, which is 19.58, times 100. And similarly, you do the percent RSD for the pure one, whereas this one is for the ore, is equals to 0.3236 divided by the mean, which is 238. That's a definition for relative standard deviation, times 100. And so when you do those calculations, you're gonna see this is 1.68, whereas this is 3.72. Meaning, if you calculate the sampling error, then it's gonna be equals to the root of this guy, the 3.72, of course squared, because remember this is the relationship. Okay, so if at all I'm calculating the sampling error, I need to square, this guy, right? All right, minus 1.68 squared. And of course that's percent. You're talking of percent. And so when you do that, you're going to find the sampling error then is going to be 3.32%. So the next problem, maybe I'm beating this to death, is calculate the equivalence volume. Because I really want you guys to understand the equivalence volume. You use it a lot in the industry, in the volumetric titration. So that's your reaction, that's your titration reaction. And you can see it's a precipitation titration, right? It's a precipitation titration. Of course, by precipitation titration means the product is a salt. You can see it's a salt. It's precipitating. It's a salt. Okay. So you, in this case, how do you calculate, the equivalence volume? Again, remember the equivalence volume, is a point at which, or the volume at which, at which the moles of, you've added enough moles of the analyte, in this case, the phosphates, in this case the phosphates is equals to, the moles, of the lead. You've added enough volume to satisfy, that relationship. And so the moles, again, remember stoichiometry, very important, very important. So the moles of the phosphate that you use to titrate, is equals to 20 ml times 0.1 molar. So this gives you 2 millimoles. Now the moles of the lead that was used is going to be 2 millimoles, which you've already calculated there. But again, it's not at 1-to-1 stoichiometry. In this case, at 3-to-2. So I need to take 3/2, right? So 3-to-2 stoichiometry, which is going to be equals to 3 millimoles. Okay. Meaning the VE that was used, for lead is going to be equals to the 3 millimoles that I calculated, divided by the concentration of my titrant, which is that. And so it gives you 15.0 mil. And so that's the equivalence volume. Sometimes they call it the tighter volume. That's a tighter volume. That's a tighter volume. So question number 19, let me not go through the details. I think it's fairly straightforward, but I've given you the solution to that problem here. Maybe the only thing I needed to remind you is how to calculate the volume, of a cylinder. The volume of a cylinder, is calculated, by pi r squared times the height of that cylinder. And that way you can calculate the volume of the reservoir, of what you're trying to fluoridate. So very important, very practical fluoridation of water, which is a common thing that we do for any potable water, in our homes. They do fluoridation. And so I've solved it for you. Take note of how it's being done. So my last problem here is a titration reaction, but in this case we are doing acid-base titration. You can see actually it's very similar, to question number 14, because the purpose of this problem is for you, the purpose is to quantitatively simulate. Quantitatively, simulate or even derive, the titration curve. The titration curve. And that way you see, the chemical entities that are taking place in this problem. So you can see it's an acid, weak acid base problem, base titration. Of course, we all know the purpose of the titration is to determine quantitatively the unknown. And you can see that's the weak acid. Sometimes we symbolize weak acids when they are monoprotic, meaning I've got only one hydrolyzable proton. Sometimes people just use a HA, meaning H is only one hydrolyzable proton, A is a conjugate base. It's easier. So this is a chloroacetic acid. Chloroacetic acid. And that's a symbol that we're going to use for a monoprotic acid. And chloroacetic acid, you can see, is a monoprotic acid. We've got only one hydrolyzable proton. All right. And you can see that I'm reacting it with a strong base, as I should. You never react a weak acid and a weak base. You never do that. It won't give you any end point at all. So you have to react it with a strong base, sodium hydroxide, that's my titrant. And it's a neutralization reaction, the product is water. But in this case, remember, I also gonna have the conjugate base here, as a product, right? The conjugate base. All right. So the first thing I need to do, as I did in question number 14, determine the equivalence volume. Determine equivalence volume. Or VE. I'm gonna call it VE. And of course, I've beaten this to death. The moles, equivalence volume means the moles of the acid or the analyte, should be equals to, the moles of the titrant. Moles of OH minus, which is a titrant. And so I already have it, in my problem there. The moles of the analyte is 5.0 mil. Multiplied by 0.1 as a mole is gonna be equals to the equivalence volume multiplied by the 0.1 molar. And so the VE then of OH, of course, that's a titrant, as the equivalence volume, is gonna be equals to 25.00 mil. Okay. So you've been asked to determine the pH. You've been asked to determine the pH also at 0.00 mil of OH, meaning at the beginning, when nothing has been added, no base has been added. So remember what's happening in this case. No base has been added. You have a weak acid essentially in water, and what happens? You've got dissociation. You've got dissociation, acid dissociation, giving you that. It's an acid dissociation problem, at that point. And how do you determine the pH, the hydronium ion concentration? Well, it's just simply calculating, the acid dissociation, relationship here, which is that, divided by the HA. I think we all know that. It's a one-to-one stoichiometry, meaning is x squared, divided by the formal concentration of this minus x. I think by now you guys know this, yeah. And so you can solve or plug in the numbers. That's that, x squared, the formal concentration that you started with, was 0.1 minus x. And then now you can solve this problem, okay? Now, you should solve a quadratic relationship here, quadratic formula, quadratic equation. Solve the quadratic equation. And when you do the expansion, in this case, you're going to see is 1.36 times 10 to power minus 3x. That's when you take this multiplied by this. And of course, there's x squared plus, and then minus minus 1.36 times 10 to power minus 4 is equals to 0. And now you can solve the quadratic equation. And when you do, you're going to find x is equals to h plus, which is very close to 0. Just confirm this, 116 molar. And when you take the negative log, and of course the negative log of hydronium ion, that's a definition of pH. If you take the negative log of that, you're gonna see the answer is 1.93. Now maybe somebody is asking, why didn't we neglect this x like we've always done? Why didn't we say this is equals to approximately that? The reason we did that is because the Ka is fairly large, and so the dissociation in this case is fairly significant. The K for this reaction is fairly large, and so you're gonna be making quite a bit of hydronium ion in this case. But nonetheless, you're gonna see it's very close, to that number, even when you solve the quadratic formula. So the next point, is at deriving the pH at after adding 5 ml, of the base? That's the next question. You're gonna see again the reaction that is taking place, is I've got my weak acid, my chloroacetic acid, and I'm reacting it with a strong base, which is my titrant, to give me water, plus the conjugate base. And of course you can see initially what I had here, was 25 ml of the sample times my concentration was 0.1, and so my number of moles, was 2.5 millimoles. Now, how much have I added? Remember, I've added 5 ml of my titrant, and the concentration of the titrant is known. It has to be, which is 0.5, millimoles. Remember, for every mole of the titrant I add, there is a change. And so the change is 2.5 millimoles minus 0.5 millimoles. And then in this case, the change is minus 0.5 millimoles. All of it is consumed. And then I have made plus 0.5 millimoles of my product. And of course, I've made the same amount of water, but I don't care about how much water I've made. And so my equilibrium amounts then is going to be 2.0 millimoles, but all of this has been consumed. 0.5 minus 0.5, so approximately 0 millimoles, and I have 0.5 millimoles, of my conjugate base. So see, you have some HA that is present, but you also have some conjugate base that is present. And so what do you have now? You've got a weak acid, you got a weak base. So what is that? It's a buffer. That's a buffer. That's a buffer that you've just made. Now, how do you calculate, the pH of a buffer? You do that using the Henderson-Hasselbalch equation, and all of us know how that looks like, pH is equals to the pKa plus the log of the base divided by the log of the acid. And then now what you're gonna need to do is just substitute the constants here. The pKa is known is 1.36 times 10 to the power minus 3, and you've just calculated, the amount of the base, which is 0.5 millimoles, and you have the amount of acid, 2.0 millimoles. And when you solve that problem, you're gonna see the pH is equals to 2.26. So the next point, in the calibration, although it's not in the problem, but I've just inserted it. What about a 12.5 ml of OH added? Now you can see this is half the equivalence volume. Remember, the equivalence volume was 25. And so this is half the equivalence volume. And you can remember in my lecture way when I said this is a very important landmark when you're doing acid-base titration. So let's take a look, at what's happening at this position, that point. So you've got the chloroacetic acid again. You're reacting it with the base to give you the conjugate base, plus water. Initially, remember, I've got 2.5 millimoles, right? Because I've got, the 25 ml and the concentration is 0.1. I have added, So the next point, you know, in the calibration, in the titration here, is at 25.00 mil. Okay, so sorry, I think we've already, yes, that's what you're doing, you know, at 25.00 mil. And you can see this is equivalence volume. Okay. Now at the equivalence volume, you know, we know that our reaction, you know, which I'll write it again, has gone to completion. You know, meaning all we have is a conjugate base, because the reaction has gone to completion. All we have, you know, is a conjugate base. Okay. Now we know that a conjugate base undergoes hydrolysis. It undergoes hydrolysis. Take note of this. Now is a Kb. Okay. Very important landmark again. The equivalence volume. Okay, sort of the opposite happens. You've got the products that are undergoing hydrolysis in this case to give you the HA plus the OH minus. Okay, and of course at this point then you just need to determine you know, the concentration based on the hydrolysis reaction, which is that the product divided by, you know, the reactants, which is that. Okay, maybe somebody is asking then, you know, how do we calculate the Kb? Remember, and this is important, you know, Kw, the autoprotolysis constant of water, is equals to Kb, you know, the base dissociation, the base constant, the base hydrolysis constant multiplied by the Ka. Very important. Same thing as, if you take the negative log of both sides, you get pKa plus pKb. Very important. And I think we all know that 14 is equals to pKa plus pKb, right? Now, from our problem here, we already knew the pKa is equals to that, and so we can easily calculate, you know, the pKb. And so you can easily calculate, you know, the pKb. And so the pKb then is equals to 11.13. And so if at all you want to know the Kb is equals to 10 raised to 11.13, you know, which is equals to 7.4 times 10 to the power minus 12. And so lastly, you know, you can plug things in the, you know, the equilibrium expression Kb, which is known, 7.4 times 10 to the power minus 12 is equals to, you know, the x squared. It's a one-to-one stoichiometry again, right? You know, this relationship is a one-to-one stoichiometry, meaning that x, you know, that x, that's a form of concentration, you know, the one that we started with, which is equals to the formal concentration, remember, which is 0.1 molar, okay, because all the HA that we initially started with has been converted, you know, to the A minus. We started with 0.1, all of it has been converted, you know, to 0.1, to the conjugate base, and that's why we are putting it here. However, we've diluted it, you know, because we initially started with 25 mil, but we've added 25 mil more, and so we've diluted it, all right? And then we minus x, you know, as we normally do, because it's a base hydrolysis reaction. And so you're going to see the x then that you saw from this relationship is equals to the negative 0 OH, which is equals to the root of 7.4 times 10 to power minus 12 times 0.05. And I hope that's clear, because remember we made the assumption this is 0.05 minus x, and we've made the assumption that is approximately equals to 0.05, because this one is gonna be very, very small. Okay, and it would be true that it's gonna be very, very small, because the Ka, or rather the Kb, is very, very small in this case. Okay, and so the pOH then is equals to the negative log of 6.06 times 10 to power minus 7, which is what you calculate up there. Okay, and you're gonna see it equals to 6.21. And so the pH then is equals to pKw, which is 14 really, minus the pOH. And the pOH, I've just said is 6.21. And so the answer that you get then is 7.29. And so that's a pH, at equilibrium point. Lastly, what is a pH at 32.0 mil? So take note of this. We have added 32 mil, which is more than the 25 mil at the equivalence volume. At the equivalence volume, that's when we consumed all the chloride, that was present. Meaning we've added 7.0 mil more after equivalence volume. Okay. Now, at equivalence, remember what we said. We just have, the A minus, which is a very weak acid. And what we are doing now is just simply adding strong base to a very weak acid. Okay. Meaning we can just simply neglect the effect of the weak acid and just imagine we are adding strong base to water. So just assume, which is true, we are adding OH to water. Okay. And so the concentration then of the OH that we are adding to the very, very weak base is this, 7 mil is what we've added in excess after we got the water. And I hope that's fairly straightforward, because you can see in our problem here the titration reaction. In this case, the titration reaction, we are making the water largely, and we are adding a very weak, we are adding very strong base, to just water with a very weak acid, divided by the total volume, which is 25. That's what we started with, plus the 32. Okay, and that's the dilution formula, sometimes we call it, multiplied by the 0.1, which is the concentration, of the OH minus. Okay, and so you're gonna see when you do that, you get 0.0122 molar. 0.122 molar. You take the negative log of that, and what you get really, is the 1.91. Okay. Now that is the pOH. 1.91. So the pH really is equals to 14 minus 1.91, which gives you 12.089, and that's a pH, at a volume of 32. So if you do the curve that you've been asked to plot, the titration curve, you can see the pH is increasing as you add the base. The pH is increasing as you add the base, with the midpoint here, being the VE at 25 mil. And remember the other landmark here, the VE half the equivalence volume, very important landmark. pH is equals to pKa, a very important landmark there. So please review the last lecture that I gave, already in the videos on the polyprotic acids and bases. Very important, for your midterms. Yeah? But again, I think I gave a fairly clear lecture about how you determine the pH of polyprotic acids, when they are fully protonated, the amphiprotic species, and the fully deprotonated species.